compressed into about 2 days. That's all right. What questions do we have? Sorry, I said that right in your face, didn't I? I have something for you in my office. Are you going to be in my office later? Or no? Okay. Tomorrow? Okay. Just remind me that I have something to give to you. Okay. It's not a bad thing. It's just have something. I forgot to pick it up on the way out. All right. Any questions about anything at all before we get going? All right. So last time we talked about the vector space axioms. So in order to be called a vector space, we needed to satisfy all 10 of those properties that we talked about last time. We had showed that our ordinary Euclidean vectors, our Rn vectors, those satisfy those axioms under addition and scalar multiplications. So those are vector spaces. But again, the idea for being able to abstract is to be able to treat other things like they are vectors. So the examples that we talked about, the examples that we talked about last time, besides Euclidean vector space, is a set of n by n matrices. So we know that if we look at the arithmetic properties of matrices under addition and scalar multiplication, they satisfy all 10 of those properties that we talked about last time. So that would be a vector space, and in that case, in that space, your matrices are vectors. Pardon me, we also talked about our polynomials of a given degree or less. So we refer to that as p sub n. We also talked about why we want to make sure we said degree n or less, because it's possible that you could knock the degree down by doing addition. All right. So in that case, we might want to think about our polynomials as being vectors. Okay. So satisfies the axioms of being a vector space. The polynomials in that case would be the vectors in that vector space. One of the reasons why you might want to do that is that polynomials are exceptionally nice functions, right? They're continuous everywhere. They're differentiable everywhere. You can do polynomials by just adding. Basically, it's just adding, right? Any operation you do with a polynomial is just adding. Subtraction is just adding backwards. Multiplying is just adding fast, right? Exponentiation is just adding really fast. It's all just adding when you do polynomials, which means that polynomials behave nicely with computers because I can add, subtract, multiply, divide just by turning switches on and off, which is all a computer or a calculator can do, right? Turn a switch on, turn a switch off. It has to do those in combination to do all the operations that it does. What a computer cannot do exactly is take the sign of a number, right? Can't do e to a number. So what's built into calculators are really good approximations using polynomials. So we need to use those vector properties of polynomials to get those approximations. That's a more advanced topic, but that's kind of the idea about why we might want to use polynomials as vectors. We also talked about function spaces, function vector spaces. One of the ones that we did last time talked about the continuous functions on an interval. We also talked about being a certain number of times differentiable on an interval. Okay. But again, in that case, in that space, your functions would be vector spaces. If you've had differential equations, you use functions as vectors when you write solutions to differential equations. So in any event, that's why we're doing this abstraction. So we can treat these different objects as vectors, and they all have similar properties as spaces so that we can apply them in different situations. All right, so we'll do some weird examples because the weird ones are the fun ones. But when we do different things later on, we'll go back to familiar things under familiar operations. All right, so in this example, we've got ordinary addition for our vectors from R3, but we're going to define scalar multiplication as just take the scalar, multiply by the first component, don't multiply by the other two. Okay, that's how it's going to be defined in this case. Now remember, we've got 10 axioms that we need to check in order to make sure that something is a vector space. But if we're doing ordinary addition for R3, do I need to really check anything in the first 5? No, because we already checked that, right? We know that our axioms 1 through 5 are satisfied. Because we're using ordinary addition. In R3. We've already proven that ordinary addition of 3-dimensional vectors satisfies the first 5 properties, right? The only thing that's changing here is how we're defining scalar multiplication. So since we changed the scalar multiplication, we need to check whether or not the scalar multiplication actually works, satisfies those axioms or not. Now again, in order to be a vector space, it has to satisfy all 10 axioms. If you find an axiom that it doesn't satisfy, then it's not a vector space. Okay. All right, so let's just check the other ones. Remember that the 6th axiom is that closure axiom, right? So if I take a scalar, I used k in this case instead of a c, it doesn't matter. But if I take a scalar, I'll use a c just as a different letter, and multiply it by an x1, x2, x3, and I know I'm changing the letters on purpose here. What is that equal to according to our definition? Just what's the answer if I do the scalar multiplication? How we are defining scalar multiplication in this example. Good, x2, x3. Good. We're not changing anything from the definition here. We're not changing the size of the vector. We're just saying that when I do the scalar, I'm not taking it to each component. I'm only doing the first component. Right? Remember, the first one is the closure axiom. Is this back in R3 again? Yeah, this is a 3-dimensional vector. There's no issues there. So axiom 6 holds. Axiom 7 was distributivity axiom. Yes. Yep. Yep. It's because it's the ordinary addition. We already proved that they hold because it's ordinary addition. We didn't change the addition to be something weird, so I didn't need to bother checking it. We did that back in the section 4.1, right? Because when we had all those 10 properties that we wrote down in 4.1, we know that the axioms 1 through 5 hold in the Euclidean spaces. We already know that. Okay. All right, so I need to check whatever, doesn't matter what word I'm trying to say. Does scalar multiplication distribute over vector sums, right? Probably the easiest way to check that is just to do each one, right? In the first case, I've written down a constant times the sum of 2 vectors. In the second case, I've written down the constant times each of the vectors and then add. Okay. So in the first case, what do I do first? The multiplication or the addition? Addition, right? We do the addition first. Okay, because it's inside brackets. Is this weird addition or just ordinary addition? Ordinary, so we're just going to add them together. So we would have c times x1 plus y1, x2 plus y2, x3 plus y3. Now when we multiply, what do we get?
Cx1 plus y1, cx2 plus y2.
Careful.
What? Oh no, it's just x2.
Good. And x3 plus y3. Good. Because remember, that's the weird scalar multiplication, right? We're just saying take the scalar times the first component, leave the other 2 alone. Right? Because it's defined for you. They'll tell you that it's weird. Okay. In fact, you'll notice that I've got a slightly different notation here. Some books use that notation to say, hey, by the way, this might be weird. That's why I have it there. Okay. So they'll use like a plus. If the addition's weird, they'll do a plus with a circle around it. And if the scalar multiplication is weird, they'll do a dot with a circle around it. Okay. All right. What about the other case? What are we going to do first in the next one? Multiply. What do we get for the first one? CX1. Oops. X2, X3. And the other one will be the same thing, but with Y's, right? And then we add, what do we end up with? I can write today. Are these two the same? Yeah, they are equal, right? Because you can think about it either way. In the first case, I could distribute the C through because that's just ordinary real number multiplication, right? At this point. Or I can think about factoring out a C. Either way, I can see that those two things are equal, right? So our seventh axiom holds here. Eight is the distributivity axiom the other way, right? It's C plus D times X1, X2, X3, or C X1, X2, X3 plus D X1, X2, X3, or yeah, X3. Yes. I've just changed the letters. You could use XYZ if you wanted to, but I could use X1, Y1, Z1, and X2, Y2, Z2 if you wanted to. It doesn't matter. I just changed the letters. I also changed the K to a C. All right. What do we do in the first case? Yeah, they just multiply the C plus D to the X1, right? The C plus D is a scalar, so I'm going to take it and multiply it to the X1 and leave the other two alone, right? And that's it. That's all we get. What do we do in the next one? You got to multiply it through first and then add, right? So what do you get for the first one? Good. And the second one? Okay. And now what do you get when you add? Good. Now, are these two answers the same? No, they're not. Right? That's 2x2 and 2x3, isn't it? Okay. So axiom 8 fails. So this is not a vector space. Remember, I told you when we first talked about the axioms and what they're really saying is that, remember again, this plus sign in the middle between these two things. Since C is a scalar and D is a scalar, this is ordinary real number addition, right? That's just regular old addition of real numbers. But this sign here is not real number addition, right? This sign right here is I'm taking this vector and adding it to this vector. Okay, so we really are changing what we're doing with adding. So our scalar multiplication has to be well defined so that I can switch my adding from real number ordinary addition all the time to vector addition that might be weird. Okay, so that has to be behaved nicely. This one doesn't behave nicely, so it's not a vector space. Questions on just going through the axioms here? We'll just do basically what am I doing? I'm looking at both sides and seeing if they're equal, right? In this case, it wasn't.
Once one axiom fails, the whole thing.
The whole thing's not a vector space, so you can stop. And if you would have found out which one failed to start with, you could have just done the one, right? If I would have recognized that 8 was going to fail ahead of time, I wouldn't have needed to do 6 and 7. Yes. Well, remember, we're following the axioms, right? We have to test whether all 10 of those are true. In order for it to be a vector space, all 10 of those have to be true. Okay, so there's not anything that we're picking and choosing. I literally have to use each of those. What I'm doing at each stage is, I'm just computing the left side, and I'm computing the right side and see if they match. Yeah. Okay. Other questions on that? Well, we're going to do more here. Are there other questions on that? Let's do another one. Set of the subset of all of 2x2 matrices that are invertible under ordinary scalar multiplication, but we've got a weird addition defined, and this is what I was mentioning with the notation, right? As I'm defining a weird addition, I'm using a kind of that circle around it to tell you, hey, by the way, this might be weird. Okay. We're going to define addition as multiplication. And we're going to check whether or not this is a vector space. Good. What do you think? Yes or no?
What do you mean by
We're literally saying the word addition now means multiplication. Remember, addition is just a word for some operation, right? Okay, so now I've just said the addition now means multiplication. Does it work? That's the idea. Okay. You already do this. You all look at me like I'm crazy, but you already do this. You know different things that addition means, right? You know addition of real numbers. Did that back in grade school, right? But then you went to high school. What did you start adding? Polynomials. That's a different addition, right? Same word, different addition, right? Many of you have had physics. You talk about adding vectors. Same word, different addition, right? Okay? So I'm just using same word, saying this is now a different addition. Okay? You've done it. You just don't think about doing it, right? But you've done it all your life. You've changed the word to mean the same thing, right? In this case, we're just saying, hey, addition now really just means multiplication. Same idea. Now, it may not work. That's kind of the other part, right? Just because I say it's this doesn't mean it works. Okay. What do you think? Do you think this is going to work? Probably not. What's not going to work? What's that? The commutativity of addition, right? Remember your axiom 2 says what? Axiom 2 says that we have to have u plus v equals v plus u, right? And that has to be for all vectors that we pick, correct? So if I use a capital V to denote my vector space, that's what axiom 2 says we have to have, right? No matter what we pick, I have to be able to do the operation in either order, correct? Okay. Can you find me an example that doesn't work? In invertible 2x2 matrices, can you find me an example that doesn't work? Can you find me two examples of two invertible matrices? You should be able to find me lots of examples of invertible matrices.
Can I just guess?
Sure, you can guess. My guess is
17368543.
okay. Sure, why not? Are those invertible? Because remember, it says it was a subset that are invertible. How can I check that those are invertible? What do you need to do to check they're invertible?
Or just if AD minus BC.
Yeah, take the determinant, right? The determinants are a numeric check to see if it's invertible or not, right? Are those determinants, either one of those determinants 0? No, the first one is what? 6 minus 21, so you get negative 15. The other one's 24 minus 20, you get 4. Yeah, so they're both invertible. So you made a good guess so far. You picked two invertible matrices. So that was good. Okay. I want to check that they don't commute, correct? Yeah. Yeah, they don't commute, right? So let's just do the product in either order. Do 1736, 8543 and multiply it, and then do the other way around. Now, if these do commute, I'll be shocked. Usually, if you pick two at random, and they're not going to commute. If they do, I'll be surprised. What do you get when you multiply these together? Let's just do the upper left corner. What do you get in the upper left corner? What do you get in the upper left corner of the other one? 23? I agree. Does it matter what the other ones are? No. Those are not equal, are they? Okay. So these are not equal. So axiom 2 fails. We showed that it failed by finding a counterexample. Notice in the other one, we didn't find a counterexample necessarily, but we can tell that 2x2 is not going to be the same thing as x2 unless your x2 is equal to 0, right? Change your x2, it's not going to be equal. Any other ones you can think of that might fail? 2 certainly fails. Associativity is okay. 3 is okay because we know that matrix multiplication is associative, so 3 won't. So 3 is fine. Assuming that it was commutative, assuming that you had something that commuted, would axiom 4 pass? Would you find a 0 vector? What is your 0 vector? What would be your 0 vector under matrix multiplication, assuming that it satisfied the other pieces? What would be your 0 vector? What is the identity? Yeah, the identity matrix, right? That is the identity in that case, correct? So in that case, your identity matrix would be the 0 vector. What would be your additive inverse? This is the inverse of the matrix, right? The multiplicative inverse of the matrix, because again, we said addition is now multiplication. Okay. So 3, 4, and 5 are fine. 2 is bad, but 3, 4, and 5 are fine. Okay. Let's think about your distributivity axioms. There might be an issue there. Okay. For example, if I want to do, pardon me, if you want to do C times that sum, well, again, how are we defining sum? How are we defining addition? Multiplication. There's nothing to distribute anymore, is there?
No.
That's it. That's all we got, right? It's just the constant times the product. But what if you do it this way? What are you going to end up with? CA times CB or C squared times AB, right? Are these two equal? No. So your axiom 7 would fail too.
Oh, okay.
Yeah. Is all right?
But once one fails.
Once one fails, you're done. Yeah. But I just wanted to show you that this was all. Even if 2 were true, even if 2 didn't fail, 7 would, because of the way that your scalar multiplication works with matrix multiplication.
So would it be like if you had to, let's say we was given one of these and we had to like probably check from 1 to 10.
Mm-hmm.
Is there like ones where like you recommend them first that probably fail the fastest?
It would depend on the situation. I mean, if you've got ordinary addition, then you don't need to bother checking the ordinary part because those will be true. So then you do your scalars ones. But if you've got something that's change or addition, you might as well just start at the beginning and see what happens. This one okay? All right. What about this one? Asking this one for a reading. It leads into the next section. So it says we've got, let's ignore almost all of the words. You don't cross this out on your paper, but what if I wrote that and crossed out those words and not worried about this either? Then we're good, right? Because that's 3x3 matrices under ordinary addition and scalar multiplication, right? So assuming that it is a vector space to start with, I wouldn't need to worry about any of the axioms because I already know they're true, right? So what's really the issue that I would need to worry about? Yeah, the matrices themselves, right? I said that would be what we would really need to worry about. If I know that I have everything else is okay, I don't need to worry about 2 because I know that matrix addition is commutative. I don't need to worry about 3 because I know the associativity works, right? I don't need to worry about the scalar multiplication ones. What I really need to worry about are those closure ones, right? Remember the 1 and 6 are the closure ones, right? So remember, closure says that if I take, pardon me, if I take 2 vectors in my vector space and add them back again, oops, not change the letters here. I need to be back in my vector space again, right? So if I just take 2 vectors in my vector space, in this case, 2 matrices that have the appropriate form. Notice what the appropriate form is, by the way. I have to have zeros there. I don't have any restrictions anywhere else, but I have to have zeros in that diamond pattern, right? That's the appropriate form in this case. When I add these 2 together, do I end up with something in that form? What do you end up with? A plus F, 0, good. Yep, and so on and so forth. I like that answer, so on and so forth. This has the appropriate form, so it's back in the vector space again, right? So axiom 1 holds. Right? What about the scalar multiplication? What if I do, I'll use a K since I've got a C up there. If I do the scalar times the matrix, what do you end up with? Ka, 0, Kb, 0, Kc, 0, Kd, 0, Ke. Is that back in the vector? Does it have the right form? Do you see zeros in that diamond pattern again? Yeah, so it's back in there again. So axiom 6 holds, right? So 1 and 6 hold for the closure. We already said that ordinary addition satisfies 2 and 3 without any issues because I know that ordinary addition of matrices is commutative and it's associative. I know that scalar multiplication is going to behave nicely because we already know that scalar multiplication behaves nicely for all matrices in general, right? Still need to worry about 4 and 5. Because remember, 4 and 5 is the 0 vector, and 5 is the additive inverses, right? What is the 0 vector in this in your M303? What is the 0 vector? It's ordinary addition, so what's the 0 vector? Which matrix is it? It's the 0 matrix, right? It's just the one with all zeros in it, isn't it? Okay, does that fit that form? The matrix of all zeros, does it fit that form? Yeah, because the important part is that I have zeros in that diamond pattern, right? The A, B, C, D, E can be anything else that you want. So the 0 vector is back in there, so axiom 4 is good. All right? Without any questions. What about additive inverses? How do you take the additive inverse of a matrix? What do you do? Yeah, just do the negative of each of the entries, right? Do the opposite of each of the entries. Does that have the right form then too? Yeah, because the opposite of 0 is 0, correct? Okay. So the axiom 4 and 5 also work. We could have also gotten axiom 4 and 5 for free. We proved this before, and I think it probably was it might have been one of your homework problems as well. If I take 0 times any vector, and I'm in a vector space, what do we know happens? You get the 0 vector, right? Right. I know that this was closed under scalar multiplication, right? What scalar could I use here then to make sure that the 0 vector is in there? What could I multiply the matrix by to make sure the 0 vector is in there? 0, good. What do you think -1 times a vector is going to end up being? Yeah, the negative, yeah, it's going to be the additive inverse, right? And the way we prove that, I don't think we proved this, so let's see if we can. Using the axioms to show that this really is the additive inverse. If this is going to be the additive inverse, what answer should I get here when I'm done? 0, right? I better get the 0 vector, correct? Okay. So to that end, what axiom allows me to do what I just did there? Yeah, that was number 10, right? That was axiom 10 that allows me to do that. Yeah, the scalar identity. Exactly right. That's the 10th one. Good. What axiom allows me to do this one? What did I do from here to here? What does it look like I did from here to here? Yeah, I pulled it out, didn't I? Which one was that one? It's a distributive property, isn't it? Okay. What are these? What kind of objects are these in here? They're scalars, they're real numbers. So what does this plus sign mean here? Just add, right? What do you get when you add those two together? 0. And what we just say 0 times that vector was? 0 vector. So did I just show that this was the inverse? Yes. Sure did. Yeah. Good. Okay. So why would I not need to check axiom 5 here? What scalar could I multiply here to make sure that the additive inverse is back in my vector space? What scalar could we have used here to get the additive inverse of this vector? Negative 1, right? I'm telling you, it's a scalar. Right? I need to multiply by -1 to get it, right? Yeah. All right. So the idea behind this is that if I have, and this is going to be what we're going to talk about here in the next section, what if we have a subset of something that we know is already a vector space? Then all we really need to do is check the closure axioms to see that it's also a vector space. The other ones will get satisfied for free. We're going to expand on that, but that was one of the reasons why I want to do this example. If I have a subset of something that I know is a vector space, it cuts down my work. Okay? All right. So let's go through and write down some of these properties of vector spaces. that and let's make sure I have them in the same order the book does. Don't remember what the fifth one was going to be here. Forgot what I'm going to do in here. Anyway, so some of these properties we've already talked about. This one we've already proven, right? This is true for any vector space that you have. We also said that if I have a constant times the zero vector, what do we get? Zero vector. I think that was in your homework, wasn't it? Yeah. Okay. Notice that the proof is the same for both of those, right? This one, you start with the side that's got two objects in it and rewrite the zero cleverly, right? This one you would take 0 times v and write it as 0 plus 0 times v, right? This one you would take c times the zero vector and write it as c times the zero vector plus the zero vector. Why would you do that? What can you do in each equation? What can you do on the right-hand side that you couldn't do to start with? Well, there's one step you'll do before you add something to both sides. What can I do now on the right side of each of those?
Oh,
Distribute. Yeah, that was the word I was looking for. I can distribute now, right? In both cases, I now can distribute something. Right? And then you can add something to both sides after that. But in both cases, and that's the crux of the proof, in both cases, I can distribute. That's why we rewrite it cleverly.
So in both cases, you would add the additive inverse.
Yes, in both cases, you add the additive inverse of the vector to both sides. Yep, and then cancel. Yep. Mm-hmm. Say that again. Not in necessarily in every single problem, but for example, what we just talked about a minute ago, I think your book labels this as number 4, and I'm still trying to figure out what I had for number 5. When we had the -1 times this vector, says the same thing as that, right? We didn't do something to try to distribute. We said that if I want to show that this is the additive inverse, then I need to show it behaves like the additive inverse, right? So we started this one by adding it to the thing that we're saying it's the inverse of to get 0. It depends on the context. I mean, actually, I could get to this a different way. I wrote it this way. I could do it using this property. This is one way to do it, to show that it's the inverse. Do you see a clever way to get to it using this property instead? If you wanted to use this as your starting point and get to this as your ending point. Do you see a clever way? Okay, does anybody besides me see how to do it cleverly? Yeah, try this. There you go. Good. Exactly. All right. That's the same thing as 0 times v, isn't it? Because 1 plus -1 is 0, isn't it? And now again, what can we do on the left-hand side that we couldn't do before? Distribute. So I get 1 times v plus -1 times v. Right? 1 times v is just v. And then at this point, you can move your -v to the other side. So there's a couple of ways to get at it, right? This way was to show that we start with this to show that this behaves like it's the inverse of this, or you can start with a known statement and play with it. You do that too. I mean, I know this seems weird and new and odd, and I hate it, but you do this too. You did this in trig. You came up with this one, for example. Oops. Come up with that example, right? You came up with the Pythagorean identity for sine and cosine, and then you divided both sides by, say, cosine squared to get a new identity, right? Did that in trig all the time, didn't you? Start with one identity, get a new one, right? That's what we're doing here, starting with one identity and getting a new one. Another property here. You're all very happy about this today. Oh, sorry, not times zero. If a constant, a scalar times a vector gives you the zero vector, then either the constant was zero or the vector was the zero vector. That works for every single vector space as well. That's a zero factor property kind of idea that you're used to. Right? At least I hope you're used to using a zero factor property. Just to go through this proof real quick, because I know you all love proofs. It's part of the point of this class is to do proofs. All right. Anyway, the reason why I want to do this one in particular is because it illustrates a proof technique. Well, certainly, the conclusions are either C is 0 or the vector is, right? Well, certainly, if C is equal to 0, then I have 0 times V is equal to the 0 vector. We already know that, right? So let's assume, or let's suppose, that C is not 0. We need to show that V is the 0 vector, right? We agree with that? Okay. So let's do that. What is that equal to? V. But now that C is not 0, we can divide by it, right? So I can rewrite my 1. I'm running out of space. Erase this here because we don't need trig. We don't need no sneaking trig. Okay. Oops. Get that, right? Actually, I should have written it as 1 over C times C. I know that this is real number multiplication, so I can reorder it. We can now reassociate and get 1 over C times V. But what are we assuming? What's the hypothesis that we're assuming here? What's C times V equal to? 0. So now I have 1 over C times 0 is V, and certainly 1 over C times 0 is going to be the 0 vector. I really wish I remembered what I was going to put in number 5 there. I forgot what I was going to put in number 5. It might have been this one. And we talked about this before. If I do the additive inverse, and I think we mentioned this the other day. If I do the additive inverse of the additive inverse, what do I end up back at? Back at V again, right? We can go ahead and do this proof real quick as well. This is not bad. From what we proved up here, what I've got circled, I can do that twice. How can I rewrite that negative out in front? Using this property that's circled up here above it. How can I rewrite that negative out in front? a negative 1 times negative v, right? How can you rewrite that negative? Yep. Right, now I've got negative 1 times negative 1. Notice that this negative 1 currently is with the v. I want it with this negative 1. How do I do that? Reassociate, good. And now inside that bigger set of parentheses, what kind of thing do we have? Just real number multiplication. Negative 1 times negative 1 is 1. And then 1 times v is just v. Does that make sense? This kind of idea here allows you to prove things like a negative times a negative is a positive. You were probably told way back when, it's like, well, you multiply two negatives, you get a positive. Well, you can actually prove it using this type of property. Questions on that at all? All right. That finishes up this particular section. We will get into subspaces next time, which is what I was talking about, that one example we did. I said as a precursor to the next section. We'll talk about that next time on Friday. Is today Wednesday? Goodness gracious, it feels like it's been a long week. All right. See you on Friday. I was going to say have a good weekend, but still got another couple days to go before then.